Hello and welcome to the presentation on breaking iOS applications with Ida and Frida. Compared to the previous presentation that I did on main difference with working with iOS compared to Android is that iOS is all written in Objective-C instead of Java. Main difference will be that we can't directly hook classes, we can only hook function symbols, and we cannot just simply get an application package from the internet because IPAs are mostly encrypted for the device. Additionally, application on the phone must be debuggable. That means that you need to have a jailbreak jailbroken device, or you need to make a debuggable application that you can install on your phone. Main process of reversing an iOS application will be in installing application from the App Store is straightforward, and dumping application from the iPhone. For this demonstration, I have a phone with me here that I will be dumping applications from. Unlike Android, there are almost no emulators for iPhones, so we'll have to do what we can do with physical devices. For dumping applications, we will be using a program called Frida iOS dump, which is freely available on the GitHub, and you can use it with Frida to dump almost any applications from the iPhone. The problem is it's highly likely that you won't be able to do it through Windows. That's why we will be using virtual machine with Linux installed. Uh, if it will run, yeah, great. Stuck. It will restart in a bit, so yep, sorry for that. Uh, then, uh, well, dumping application is pretty straightforward. You just launch the application and launch the program that will basically dump the files. I can show it to you via the browser probably. Okay, yeah. Basically, it will start dumping all the inner repositories and the dynamic libs from frameworks, and will give you out a packed application like this, which you can unpack and directly access the main library, named, for example, like this. Next process will be next stage will be is decompiling application with IDA. Our application will be I pre-decompiled an application because of the lengthy process of decompilation. So as you can see, you get the text view of the application with all the classes that you can connect to via Frida. For example, for this application, let's try to get an a CocoDB encryption, which is interestingly why it's called close to the same. Will you start function searching here? Sorry for that. I will relaunch the application because somehow everything decided to get stuck today. Um, okay, that will preloaded library decided to just die. So we will decompile from the beginning. Sorry for that, everything breaks for me today. So basically you just, if you know how to work with sorry, if you know how IDA works, you just put it inside the application and it will start decompiling it. Currently it's just creating Objective-C classes. It will take a bit of a second. For now I will switch back to the presentation to explain the next stage in our work is basically instrumenting and extracting data from application using Frida. Most of the work we will be doing is with is using Frida trace. Frida trace is not something that we were able to use in Android because of Java compatibility, but in iOS it's freely available and really powerful. Most of the local Frida and Frida trace commands will run Python on the local machine and call something on an iPhone while creating the separate thread for tracing the application. In instrumenting iOS applications, it's mainly two keys that we will be using for instrumenting classes is -i. that includes functions from shared libraries, and -m that includes methods from names exposed by the Objective-C runtime. This will allow us to analyze function arguments because, for example, interceptor can change values on enter and on leave of the function. Same can be done with handlers inside of the Frida trace. Additionally, so the same handlers can access functions arguments, and they are mapped into the args array with args0, args1, and etc. Being mapped into the argument registers inside of the process. It is also, it says it is architecture independent. Additionally, we can also access registers with this .context.x0 if we need to access the exact register that we want to be able to modify. So let's look at the Ghidra. As we can see, it's right now running through the code. As soon as we get the main code, it will be doing Objective-C renaming. It should take a bit of like 30 seconds or so. While at it, I will show you the Frida functionality. Basically, how we can instrument the classes. If you can see, we have Frida trace, the application that we will try to access, to attach, because Frida trace directly is attaching. Then we, for example, want to access the shared libraries of encryption functions. As soon as we launch an application on the phone, here, and attach to it, we can see the okay, unable to spawn. Nice. Probably not the APK name, but direct name. Yes. Now we can instrument, and we see all the calls for the application from the encryption. For example, decryption and encryption will call ccrypt library from the inside of the lib common crypto dylib. Okay, let's try the same, and let's try to instrument other interesting library, which is called sec item copy matching. Which is library that is responsible for getting keys from the key store, from the keychain inside of the iPhone. We will be doing instrumenting manually first, then I will show the results in our proprietary Frida library that is basically basically our insiders tool, insiders. How can I say? Insiders toolkit that basically automates all the Frida tracing. Okay, the Frida decided to finish most of the work. Now we can find the library. Yeah, as we can see, the CocoDB library is very big. In terms of my previous analysis, it's mostly CocoDAO not CocoDAO factory. CC user default here. CC user default object by key. One of this function is usually responsible for getting the key and decrypting the data. For example, let's intercept one of those functions with Frida. This time I will be using the library directly. We will turn off keychain, and one of those functions is object encryption by key. And we had a library that is bb encryptotil. Do I have it here? No, I don't have it here because it was not that important. Okay. For example, when we launch all those three functions, they are instrumented. The program will be relaunching on my phone, and now, as we can see, we get data directly from the arguments of the application, or from the arguments of the function. Previously, since it's mostly rooted in the directly in the handlers, I will show you how it was instrumented. Let me just open a bit BB key again. Key again, get data for key. So basically we're just instrumenting all the arguments, and we can analyze the arguments directly with hex if we need it. Mainly those functions, as I remember, they are not particularly responsible for the encryption directly, so we're just changing, instrumenting a bit, and let's open up the decryption functions again, and we will access the keychain because that's the more important part in analyzing the data. If we're re-instrumenting the keychain and the and the encryption, we can see that encryption is there is an CCH MAC update and CCH MAC final. The problem is that usually there is also an additional problem that sometimes can occur, is that two handlers will be created in two different libraries. Sometimes it will be created in user lib system, libcommon_crypt, and sometimes it will be just created in libcommon_crypt in libcommon_crypto.dylib. Sometimes you need to copy those functions back and forth between the libraries to. Oh, sorry. Sometimes you need. I was showing the IDA. Sometimes you need. As you can see, sometimes it will create in. Sorry, I don't know when it will start, so I will show from the beginning then. As it was shown on the slide, Frida trace was showing with the USB tag with the name of application and with the I for ccrypt and cch mac. If we instrument it directly with by hand, we can access the data that is stored in. If it will work by hand right now. No, it won't work by hand right now. So in terms of our library that does the same thing as the tracing, we can, as you can see, we can access the data, which is basically just a big list of data. Most of the libraries are instrumented, most of the hooks are instrumented already. I will show you a bit later how they are instrumented. But as you can see, we can just access the data directly, data length, key that was used for encryption, and the MAC key that that was used for encryption and decryption inside of the application, because most of the iOS applications use ccrypt system library to encrypt, which is those hooks: cch mac, cch mac init, cch mac update, final, and ccrypt hooks. In terms of showing how it was instrumented, we just get all the arguments, and since we know how system libraries work, we just instrument the algorithm, the operation, the decryption, encryption key. We get key, and we get IV and data that was used for decryption and for encryption. In terms of how we're instrumenting the sec item copy matching function that is responsible for the keychain, is we're instrumenting it as a return object, because it always returns the objective C object, and since it was not visible, I will demonstrate how it returns the object in hooks. We will relaunch the library, and as we can see, an as dictionary object is always returned, where we can access the service data. You can see. Oh, sorry. it switches sometimes. Uh, as you can see, we can access the account, class, and service data from the application. And in terms of direct dump, we can just directly dump the application, which is which sometimes is the most important part. And in terms of the results, it usually returns, if it's hex data, it returns hex dump, which you can just decode. For example, in terms for our application, from the previous research, I was able to determine that these 64 bytes, those 64 bytes, I think, yep, group the I am the bot, genp, and with service. Those 64 bytes are the direct decrypting key that is being passed through to the application, because ccrypt function was using on the key input the same key as we get from the keychain. The biggest problem with instrumenting is directly getting the data from the IDA Pro, which will result in our A2, A3, A4, and in our parameters directly accessed. Sometimes, as we can see, it's a class pointer, which you need to which you will have to dereference to access deeper data. You can do this by using, for example, this dot pointer. Here we are doing argument. Then we dereference argument by doing read pointer. I have here exactly the dereference. Read pointer. By reading pointer, we are dereferencing the pointer, and we're accessing the class object directly to get access to the internal data in case for example, A5 will be used in here somewhere. So, in terms of instrumenting the data via trace, we can do backtraces. We can access directly, for example, the class objects inside of the security function. Oh, sorry. In terms of instrumenting, we can directly access the hex dump. We can directly access the function inside of backtraces, and we can directly access the backtraces in case we require the cold stack. In case we need to see call stack, which is really beneficial in terms of dynamic analysis and reverse engineering of data flow inside of the application. In case of static analysis, sometimes it's difficult to analyze because not all the applications right now use Objective-C. Sometimes they use most of the times almost all new applications use uh, Swift classes, which are not which cannot be accessed by M or I tags, and you will, I think, Swift applications you will be able to access them via I tag. Yeah. So those will be used. So those will be instrumented differently. This application does not use those, so there will be no demo for this application in terms of in terms of instrumenting Swift classes and Swift objects. So let me return back to the presentation. As I said previously, we can backtrace. For example, like here, console log thread backtrace map and join. That will call all that will display all the backtrace from the current entry from the current function that we're trying to trace. Backtrace is aware of backtrace is only for the current thread, but it also knows about the symbols of any shared library or system library that is being used. There is also the function of stalker that will allow you to dynamically change the application, but I don't have a demo for it now. That will have to wait for another time where where I will try to show you properly advanced Frida and advanced iOS reverse engineering, where we will be dynamically changing the application data. So if you have sorry for the a bit scuffed presentation. If you have any questions directly about the Frida, IDA, or for example, you want me to show Frida iOS dump application, which is basically it's pretty straightforward. If you're doing it via instruction, you can ask me right away.